So let me talk now about nuclear fission. Nuclear fission happens when you have a large nucleus, okay, which is called a fissile. It has an even number of protons, an odd number of neutrons. And I'll give the reason why that's so. If you add a neutron to this large nucleus, especially if the neutron is slowed down from its natural speed, it can be absorbed and give the nucleus sufficient energy so it becomes unstable and it breaks into two. And that's called nuclear fission. Okay? When it breaks into two, it gives off energy. And this is the reason we would like to use it. That is, per pound or per kilogram, this fissile has 2.3 million times more energy than coal, or oil for that matter. So the reason that you need an odd number of neutrons is if you have an odd number, neutrons have a spin, and usually they're paired, one up, one down. So if you have an odd number, there's always one that's unpaired. Therefore, if you come in with another neutron, if it's the same spin, it'll just bounce off. But if it's the opposite spin, it can be absorbed, and that releases enough extra energy to allow the thing to fission. Okay? So if we ask what kind of nuclei do we have in nature such that it's even in number of protons and odd in number of neutrons, uranium-235 is the most famous example. But uranium-235 is only 0.7% of natural uranium. Okay? Most of it is U-238. That's an even number. It's even number of protons, even number of neutrons, so it's not fissionable. If you come in with a neutron in it, it'll just eat it without fissioning. Okay? But that gives it too many neutrons. So uranium-239 turns two of those neutrons by what's called a weak interaction or beta decay into two protons and now becomes plutonium-239. Okay? In an ordinary uranium reactor, this will always happen because you have mostly uranium-235, some uranium, mostly uranium-238, a little bit of uranium-235. So the 238 automatically, about 0.4% of the uranium-235 things get converted in 238 compared to uranium-235 gets converted to plutonium-239. So if you take 0.4 times 40%, I'm sorry, times 0.7, you get roughly 0.3. You add that, that's the 1%, okay? 1%, the rest of the 99% is not used. There's another way to do this where you can turn what is not fuel into fuel, and that is thorium. Thorium has only one isotope, uranium-232, so it's even in protons, even in neutrons. If you add a neutron to it, you get an odd number, 233. Again, too many neutrons, the two neutrons turn into protons, and it becomes uranium-233. So those are the three possibilities. You either use what nature has given us, 235, or you make plutonium-239, or you make uranium-233. The reason that you can have a chain reaction is because when it fissions into these two smaller pieces, they contain too many neutrons to be happy, and they will spit out an additional 2 or 3 neutrons. The fact that 2 is bigger than 1 means you can have a chain reaction, namely one of the two can strike another fissile and cause the same thing to happen, so it just propagates like a chain, and because it's bigger than 2, you can do breeding. That is, that extra neutron above the one needed for the chain reaction can be added to 238 or 232 to make plutonium or uranium-233. Okay, so I think most people know about the chain reaction, but breeding may be new to you. The other thing that you should realize is that a nuclear reactor is not a bomb. There's no possibility that a nuclear reactor will explode like a bomb. It is always designed so that it's exactly critical mass. That is, only one of those neutrons create another fission. Okay? How to do that, I'll tell you. But basically, it's having the right amount of mass and having the right amount of surface area compared to the volume so that the excess escapes out through the surface. So it's always built, so it's subcritical, with respect to the neutrons that come out immediately. Okay? In less than 1 microsecond, it will cause another fission. There's no way to control something like that. Okay? So you always make it subcritical with respect to the prompt neutrons. Some of them come out in a delayed fashion from these fission products over a millisecond or even minutes or even hours. Those are the ones that you control or you allow nature to control. Okay? So nuclear reactors will always shut off. The problem is that they continue to put out heat after they shut off. Okay? And that is because the fission products are radioactive. Many of them are radioactive. Okay? Especially, Fukushima is made famous, iodine-131, cesium-137, strontium-90. I don't ask you to remember all these, but all of these have half-lives less than 30 years. Iodine-131 has a half-life of 8 days, so it's all gone practically today from the Fukushima accident. But it's dangerous because it gets concentrated in the thyroid. Okay? So even though it's not a gamma emitter, like cesium-137, it's still dangerous. Cesium-137 has a half-life of about 30 years, and it's dangerous because it's a gamma emitter, the most penetrating. Alphas and betas are not so serious. You can stop them with a thick rubber glove. But gamma rays are troublesome. So cesium-130, and then strontium-90. Strontium-90 is a weak gamma emitter, mostly a beta emitter, but it's dangerous because it behaves chemically like calcium. So if it gets into the milk and children drink it, they incorporate it in their bones. Okay? I only want you to remember for later, iodine, cesium, strontium. You've got to prevent them from coming out, and molten salt reactors automatically do that. So all right, so how do we use uranium-235? This is the so-called once-through fuel cycle, or the light water reactors. Light water is used because water has hydrogen. The nucleus of a hydrogen atom is just a single proton for ordinary or light water, and that's perfect for slowing down neutrons that come out very fast from the nucleus of atoms. So if you're in a submarine, it's what do you use as a moderator? Obviously water. Water's all around you. What do you use as a coolant? Water, obviously. It's all around you. Now, of course, that's salty water, which is very corrosive, but you have a nuclear reactor on board, and therefore you can desalinate by distillation any amount of water that you want, okay, and have enough for the crew to drink. That's why they can stay down for months, go 25 years in principle. They had the food. However, the water, which has a proton, sometimes will add a neutron to become heavy water, deuterium, and that absorbs that neutron enough so that you cannot use natural uranium to run a chain reaction. You have to enrich the uranium fuel, typically from 0.7% up to 3 or 5% uranium-235. The good thing about light water reactors is you have an automatic shutdown in case of a loss of coolant accident. You may know that that's the most dangerous thing that a nuclear reactor can have. If you lose the coolant, you cannot now cool the decay heat, and that leads to a meltdown. Well, what about shutting down the reactor in the first place? If you lose the coolant, you see you lose the moderator because you lost the water. The hydrogen is no longer there. So what was before a critical mass now becomes subcritical. It automatically shuts itself down. But there's still decay heat. So how much decay heat is there? At the moment of the accident, you have 6.5% full power. Now most of that decays away so that by an hour, if you can just keep things cool, it's down to 0.6%. After that, it's very slowly decaying. And you have to basically keep cooling it. Because even 0.6% of full power is thousands of times more than what the metal around it can stand unless you have a huge amount of metal. That's why it's impossible to prevent meltdowns unless you cool the reactor after it's shut down. So there are two kinds of boiling reactors. One is a boiling water reactor, which is what Fukushima was. There you use the nuclear heat to boil water, turns into steam, and you use that steam directly to drive a turbine. Okay? That is slightly dangerous because not only will the water, some of it become heavy water, but some of the heavy deuterium will become tritium. You've all heard about tritium leaks. Now that's far overblown. Tritium is probably the least dangerous of all radionuclides. All right? People make a big deal out of it because they can make a big deal out of it. Okay? They scare the public into thinking that there's a huge problem. There isn't a huge problem. Yes, all things that touch neutrons will become activated. But water is kind of the least dangerous thing you have to worry about. I guarantee you, okay, you get more radiation from your significant other when you sleep together at night than you will ever get from any radioactive. It's because each one of you has radioactive potassium in you. Okay? It's an essential part of life. Okay, so why boiling water reactors are less safe than other forms is what happens if you have a loss of coolant reactor and you have station blackout, as happened at Fukushima. No power to bring in new water. Well, eventually, things will heat up, the fuel rods will melt, and they get above 2,000 Celsius or so. The steam that is around now can be dissociated into hydrogen and oxygen. The oxygen combines with the metal. The hydrogen is free. It's a gas. Any hole that's in the system, it comes out. If that thing touches oxygen, it will cause an explosion. If you don't have a way to contain that explosion, as Fukushima did not have, you have it. Now all this radioactive stuff released in the environment because there's no containment though. The other kind of reactors, the majority of reactors in this country, are called pressurized water reactors. They are under such severe pressure that the water that touches the fuel rods directly do not turn into steam. They are above the so-called triple point. There's no distinction between liquid and gas. And they are not used to drive a turbine. Since they're not a gas, they don't expand that much. They're transferred. Their heat to them is transferred to other parts of which does boil water. So now that boiling water is no longer radioactive. That's why they're safer. Okay? That escapes. There's no radioactivity in it because it never saw any neutrons. Moreover, because it's high pressure, usually you have a dome that is designed to contain any steam explosions, and that's what happened at 3 Mile Island. Okay? There was a meltdown, but nothing escaped, hardly anything, okay? And nobody died. All right? Fukushima, nobody has died. Fukushima, you know, we just had the 1-year anniversary 2 years ago. All you saw in the news was about the accident, nuclear accident. Nothing about the tsunami and the earthquake that killed 19,000 people. Nobody actually died in Fukushima. Okay? So the U.S., because of the naval nuclear submarine program, thought that these were great reactors. They are a very fine reactor. And we exported the light water technology to the rest of the world. It was deliberate government policy, and the only people that didn't use this technology were our best friends and our worst enemies. Okay? Your best friend knows you too well to know you're not God, and your worst enemy never thought you were God in the first place. You were the devil, right? So our best friend, the Canadians, built heavy water reactors. Canadian reactors are called CANDU. CAN for Canadian, D for deuterium, U for uranium. Very fine reactors, okay? You can use natural uranium. You don't have to enrich uranium. That's a big expense. They avoided that expense. Of course, deuterium itself is very expensive. Okay, so nobody else uses it other than Canada. The Soviet Union, the former Soviet Union, used the only other material that you can moderate and has so little absorption that it doesn't it doesn't absorb neutrons, and you can use natural uranium, and that's graphite. Only heavy water, because in that case, the proton already has the neutron added to it by the Big Bang, as it turns out. And so it eats a little bit, but that only creates a little bit, tiny little bit of tritium. Okay? Graphite is the other thing. And you know, the U.S. built the atomic bomb and Germans didn't. And the reason is because Union Carbide was a better graphite company than Siemens. Okay, their graphite had enough contaminants in it so that they couldn't make a chain reaction out of natural uranium. So they tried to do it with heavy water. And when we found that out, we bombed that plant like crazy. When the bombing didn't work, we sent in commandos. When that didn't work, we sank the ferry that they were trying to ship the deuterium out. You may have all seen movies about this, right? This is part of the story. Okay, so here are the fuel cycles that are possible, in principle, if you use uranium-235, or you use plutonium-239, or you use uranium-233. The way we use it today is to envelop the uranium in a metal pellet, and then we store many pellets and rods, and then bring enough rods together so that we have a critical mass. The fuel is 5% lightly enriched uranium, and you get that because you have 2 piles of uranium, and you do isotope separation. You take some of the uranium over here, 235, and put it over here. So you fool yourself into thinking you have 5% efficiency when you burn it, but of course you have 5 times of that left over. So if you count the depleted uranium you have left over, you only have 1% efficiency, okay, total. Why don't we enrich it more? So that, well, it's because you get radiation damage. It's a solid. What that means is it has a lattice structure, but when these neutrons first come out, they often hit parts of the lattice and damage it. Okay, over time, the metal becomes brittle, it becomes leaky, and you got to stop using it before it starts leaking the radioactive fission products. So it's radiation damage that prevents you from getting 100% efficiency. Even if you were to use, 100% U-235, you would have to stop after you used about 5% of it. The other bad thing is that you create plutonium-239, which I already said you have to store for 240,000 years. Now the way around that, and this is what the nuclear power industry, conventional nuclear power industry, would like to pursue if the government allowed them, is to continue to go down this route. That is, use solid pellets, but use 100% by refabricating it. So you burn 5%, it's become damaged now. Now we go in, melt this thing, extract the good stuff, bury the bad stuff, the fission products and the other things, and enrich it some more, burn another 5%, and through refabrication, eventually, through breeding enough of the uranium-238 to use up all the uranium. So you can get 100% by refabrication. The problem is that this refabrication plants are expensive, they're few in number, so now you have lots of transport. And the public does not want you to transport radioactive elements. I don't think Palo Alto is a nuclear-free zone, but Berkeley was when I was there, okay? Berkeley also had ideas about how the Middle East should be run. Okay, so you get only fission products because you burn the plutonium-239, so the waste storage is only 300 years. With molten salt reactors, it's 100%. And the reason it's 100% is because it's a liquid. If it's a liquid, I can do chemistry. I can remove the things without melting anything. It's already molten. And I just recirculate it as a fluid. Afterwards, I add a little more fuel into it, and you can burn up 100% just through recirculation because it's a fluid. So the waste storage is only 300 years. High-grade ore is, as I said, 100 years at 6%, but if you want to use it at 100%, it will only last 6 years. So, people who are anti-nuclear have a point. What is the grand purpose of the nuclear fuel cycle that we use today? Well, if you go to plutonium-239, fast breeder reactors, and you can, the burn up is 100%, the 6 years becomes 600 years, okay, instead of 1%, right? It's 100%. Thorium is 3 to 4 times more abundant than uranium, so if you can use 100% of it and also use it all for all the energy, then it's 2,000 years, all right? Now the moderator, as I've already said in this case, is water. The coolant is water. The control is neutron-absorbing rods. And the way that works is the following. I have something that I want to maintain exactly at critical. Of course, that's very difficult, so I make it slightly supercritical, but I insert enough fuel absorbing rods in here so when I start, it's exactly critical. And you just position it so that it doesn't ramp up or down in power. Okay? Now, as the fuel is burned, it becomes more and more absorbing fission products, so you pull the rod gradually out and always maintain it exactly at critical. That's how control is maintained. What happens if electricity stops? Well, this is in a vertical position, so if the electricity stops, it automatically drops down. You need to worry about electricity stopping. You don't need to worry about gravity stopping. Okay. But don't stick your rods in this way. Okay. All right, same thing here, okay, except you don't moderate because if you moderate, the plutonium absorbs far too many neutrons. You can't breed. So you need to not moderate it, so you use fast neutrons. It needs a lot more fuel, but you keep it exactly critical. And to cool it, it can't be water, so you use something like liquid sodium, metallic sodium. Right? And that, of course, any chemist would tell you, is a little dangerous. Sodium touches air, it's on fire. Sodium touches water, you've got an explosion. Right? So we don't think that's really the best solution. Maybe we'll have to do it if molten salt reactors don't work. And the ways that you control those neutron-absorbing rods. Well, over here, the coolant is a fluoride salt. All right? It is the most electropositive thing combined with something like sodium, combined with the most electronegative thing like fluorine. So that sodium fluoride, that's not like sodium. That's what's in your toothpaste. It touches water, it doesn't explode. Touches air, it doesn't catch on fire. It's perfectly chemically stable. Moreover, the way you control it is not to control it. It controls itself. How does that work? It's a liquid. So if the reactions run too fast, it gets hotter. When a liquid gets hotter, it expands. It expands out of the reactor and slows down the reaction rate automatically by itself. Thermal regulation. If you want more power, you pump on it to cool it down. The liquid contracts, and now you have more in there, automatically maintaining the higher power level. Okay? When I saw this feature, I decided I needed to drop astronomy and help build this reactor, because that's exactly how the sun works. Okay? You don't have to worry that tomorrow the sun is going to be like what it is today. It controls itself. Nobody controls it. This reactor does the same thing. Oak Ridge, which built it, all right, the workers could go home for lunch, go home for dinner. It'll run itself. No worries. They didn't dare do it over the weekend, but they could have. They could have left it, and it would run itself. So the number that's built, that's an example of the experience, is that about 500 light water reactors were built in the civilian sector. We have 400 some today still running. We don't know how many the military has built. In terms of these fast sodium breeder reactors, 15 were built by the usual suspects, right? America, Russia, France should be in there, sorry. Germany, Japan, India, now China. Only 2 of the molten salt reactors were built. None of them were commercialized for political reasons. I can tell you if somebody asks. The first one was a disaster. It looked like crazy because they didn't have the right metal to contain it. They learned from that lesson. They invented an alloy called Hastelloy N. The next one worked like a dream. Ran 4 years without any problems. The only thing it didn't do was breed. Okay? And the reason is because if you put any metal in a breeder reactor, it will absorb neutrons. Okay? They're very efficient neutron absorbers. So if we want to build a breeder reactor, we have to do something different. Let me quickly go over this. I'm sorry to. This is a history of the number of reactors as a function of their age. Okay, So this is, reactors that are over 40 years old. And if you go backwards, that's sort of a history of the construction rate of reactors in the world. Okay, so we can see that in the beginning, reactors got built, and over a course of the first 10 years or so, they were built at such a pace that if we had kept up this trajectory, today, we'd be up at the ceiling. We wouldn't be talking about climate change. We wouldn't be talking about energy crisis. But that did not happen. Something else happened. What happened was that in the U.S., anti-nuclear activists who first protested the bomb were successful in that, and then protested against nuclear power generation in the civilian. They were very successful in closing down things or slowing things down. And by 1979, when the 3 Mile Island accident occurred, in fact, the reactor building rate in the United States had already slowed down considerably. However, Europe continued to build, so there was, especially France, and then Japan, not in Europe, but in Asia. And if we had continued on this trajectory, okay, from TMI all the way up, today also, we wouldn't have climate change to talk about, energy. But of course, what happened was Chernobyl happened. Chernobyl, let me go back. Oh, next one. Just in the next slide. I'll tell you, was a unique freak accident. Could never happen in the Western world for reasons I'll shortly go into. After Chernobyl, everything in Europe stopped, and the only level was in Asia. Places like Taiwan, South Korea, and now China, India started building reactors, and then Fukushima. All right? Where will this be in the future? No one knows. Okay? But if we want to build out thermal molten salt reactors, if we want to build out nuclear reactors, we probably cannot count down many light water reactors being built. Nevertheless, I would still argue we should try to keep the 6% because they are the match that can start the thorium fire. Okay? We need that match.